then come back to and then start when I have PowerPoint. Thanks for coming, but I figured since I was changing programs and I hadn't screenshot this, so you can see going from 2 to 0.
Yep.
Back to 2 the other way, and forward. So there's a bell trick, and you can instead, if you prefer, I think this one, do plate trick instead. So there's plate trick with a fixed shoulder, generated from the same homotopy. This will be over, and it's about 2:30, and I'll start, but I just figured since that was in there, I would start with that. You can all keep your 3D glasses and download this free program that has all kinds of cool stuff in it, like even things like space curves and torus knots and anaglyph 3D, and there's your torus knots, and you can change the number of wraps, and you can view them as point clouds. Oh, show dotted torus, there, so there you go.
Oh, lovely.
Oh, that's cool.
That should be good in 3D.
Oh, that is
That's beautiful.
This is the best thing for junior high school outreach. And then you tell them to change the number of wraps, and they'll always tell you stuff like set parameters and say 101, and instead of 5 and 2, let's do the 101, 23 torus knot, and it's like. Ooh.
Oh, wow.
Anyway, on to the talk. So this is a great program that was originated by my father, who's in the audience. And there'll be one more 3D, so keep your glasses ready, and we will start the show, hopefully. Play from current slide, I think. I want to start with the announcement that the Riemann hypothesis is solved. Put in, literally it's still happening, if you put in Riemann hypothesis in Google, as you will see me do right here, you will see Riemann hypothesis. No zeros except for real part 12. 12. Well, I just decided to go over to Wolfram Alpha and put in one with real part 1/2. And zeta of that is 0. Oh my gosh, counterexample. So anyway, so we'll start out with a counterexample to the Riemann hypothesis, literally the Riemann hypothesis according to Google, and it really happens. Try it, it's amazing. And what else about that? Thanks to Andrew Odalisco for calculating those zeros, actually. That's one of his first ones. So I actually got into this Quaternion thing when I was also working on tumor suppressing therapy, just like we heard it talk about yesterday and last year, which was so exciting, and the differential equations of cell proliferation and suppressed cell death. And we looked at a data set, this was in 2002, early precision medicine, looking at the process meter of the cells. That's really what a gene expression array is. It says how many times a protein, which is a program for a gene, which is a program for a protein, is called. And I identified 3 genes between the dormant and aggressive transition, just in the numbers. And I said, well, they're never going to be able to test whether I know what I'm doing. And they said, those 3 genes are on a pathway. And they say, just like you said, that cell death is suppressed and proliferation is accelerated. They put it in the words, the gas pedal is stuck and the brakes are broken. And they said, we can affect that, and by affecting that, they actually suppress tumor growth. Lymphoma growth was inhibited using something we came out of math. How did I get it? They said, can you explain how you got the numbers? Well, I was looking in various individual genes, pairs of genes, triples of genes, and there was one triple gene in the set of 7,000 that separated the good from the bad in 3D. But in any 2 dimensions, any 2 gene projection, they overlap like this. And Kojo, the lead scientist, pathologist, said it would be really sexy if you could move those in 3D. And I knew about virtual trackballs, but I'd never done one myself, so I had to go to the family member who had programmed virtual trackballs and help me do this. And so there it is. You can actually see there. growth, anti-apoptotic effects, and growth promoting. The brakes are broken, the gas pedal is stuck before and after, and this was really there. Inactivation of this pathway inhibits tumor growth. It was amazing to me that math and geometry could show this. And so I programmed my first virtual trackball that is actually referred to in the program, and the little black balls was all I could figure out to make axes. So I have a plus E1 and a minus E1, and if you align things along one axis, it's overlapping. And if you align along any of the three axes, it's overlapping. There's another axis I'm going to line up, early Flash action script. They're lined up, still they're overlapping, but in 3D, if you do it right from a certain perspective in 3Ds, it really shows that they're separated by those genes. And that's what I showed them, and they said, hey, let's play with this and see if we can get a therapy, and it worked. So, quick review of, or introduction. If nothing else, this might be fun. Very good thing for in teaching classes, good exercise in vector geometry. How do you actually render those points in 3D onto a screen? Okay. I'll tell you that you only really need 2 unit vectors to determine everything. Because you really only need 1 unit vector. Here's my data point in R3. Here's my camera. That's all I need to determine the point on the plane through the origin orthogonal to my line from the camera to the origin where the data point intersects. That's perspective drawing. All I need is 1 vector, this camera position. That tells me where the interpolation, I'm going to talk about interpolation later, interpolation from the viewpoint to the data point, that's a line. That's this formula, VP plus T times DP minus VP, data point, viewpoint. All I need to find is the T that makes that orthogonal to VP. Well, I take the dot product, solve the equation, there's my T, done. 1 vector gets me the point in the image plane, but that doesn't get me the point on the screen. I need 1 more. I need to know what up is. Why do I just need up? Because if I know my direction towards the screen and up, I can do a cross product this way and get my right. And so there, up tells me. And all I really need is, since I know the distance, if I just keep the distance from the camera to the origin the same, all I need is a unit vector that way. So I'm going to have an orthonormal frame that's defined by 2 vectors. So I need my up and my forward, and I can cross them to get my right, and I can scale by fixed constants to get my pixels and my camera distance. So how do I find, that's it already, same thing. The image plane, to get points, my coordinates, I just need my basis in that orthogonal plane and take the dot products with this, and then convert to pixels. How do I know that? I need my up vector, and I get my other vector from that. So to draw a point in space on the screen correctly, all I need is 2 vectors. It completes into an orthonormal frame. Okay, then, well, that's the summary of that. Aside from the viewing distance and scaling factors, all you need to render points are V forward and V up. The third is obtained by the right-handed cross product. Okay, and this is what you get out of that when we play it. Play this. Oops. Play it back. Do I have my play? Is that play? Oops.
No, that's one.
Is this not? There.
There it is.
There. Okay, so there's selected a tetrahedron. The vertex will follow the mouse, and it's path dependent. Notice when I pull to the right and back up, purple ends up on the right. When I start again and pull to the left and back up, purple will be on the other side. Yeah. So it is path dependent, but it's following my mouse. So see the path dependence and following the mouse. Later I'll show you an animation of Schumacher's arc ball, the Quaternionic virtual trackball. I implemented that the same, and I will show you that it is not path dependent and that it doesn't follow the mouse. It doubles the angle. So one pull can flip it over. That's either a feature or a bug, depending on how you feel about it. Anyway, so this is what you get. So how am I rotating things with the mouse? Am I rotating the points of this tetrahedron based on where the mouse is? Maybe. That's what a lot of people would do. A mouse point specifies a unit vector, again, in the interpolation formula. Here's a point that I convert from its pixels to its point in this plane. And then I just do that interpolation again, but instead of looking for orthogonality, I look for norm squared equals 1. Couple dot products, you got a quadratic equation. Sometimes it will intersect in 2 points, one in front, one in back. Sometimes it actually intersects in 2 points in front. You got to watch out for the horizon. That's actually the trickiest part about implementing it. Otherwise, your mouse will fall off the horizon. So that's what I discovered. So linear interpolation, the crystal ball unit sphere. That's all I'm doing is finding unit vectors from my mouse. So a mouse point specifies that. Oops. So 2 mouse points, and I think up there it says 2 mice points. I don't know, is that the plural? A mouse motion gives you 2 unit vectors. That's going to specify a rotation, right? The two unit vectors specify a 3-dimensional rotation uniquely. You could pre-rotate about this axis, post-rotate about that axis, still takes this to this. Not specified uniquely until you say it leaves the orthogonal complement alone. In this 3 dimensions, it preserves the orthogonal, the cross product. Okay. There. So if U1 is U2 or minus U2, what? It's the identity. It's the identity rotation. It takes it to itself, but anything wrapped around it. So you need more specification. Preserve the orthogonal complement, preserve the plane. So now, here is the fun part. No, it's all fun. How do you apply that rotation from your 2 unit vectors? Specified by the 2 unit vectors, it takes the first to the second and preserves the axis, the orthogonal. How do you apply that rotation to make the image rotate? A lot of people actually rotate all the points of the tetrahedron, or the icosahedron, or the 120 thing. But it turns out much simpler to reverse rotate the directions of your viewing frame. That's something I learned from family. Don't rotate them. So anytime you see something rotate on the screen today, the thing isn't rotating at all. It's just you're moving the camera backwards. Isn't that cool?
Yeah.
So that makes it pretty fast. Okay. How to apply R, V forward.
What's the factor like? Like what's the factor that you?
I mean, it's a scalar. It's a 2 or
3.
2 or 10 or something. I actually have some numbers here.
Yeah.
So how to actually apply that? So the idea is still, first of all, actually no, your question, the factor of 2 vectors versus a lot. I saw actually a workshop in one of our section meetings that said, isn't this amazing that we can, well, I guess nowadays, brute force works, but we're rotating thousands of points with the mouse. It's like, I guess, yeah, but you don't have to. It's a single object, as long as it's a single object world. And if you have multiple objects, I've realized, if you have multiple cameras to render each one independently, you can still do the same thing. Yeah, it isn't stuck to a single object world. You just have multiple cameras. I actually did that. You will see that when I do the string trick, the tangle trick. I had to use 2 cameras because I wanted the sphere to rotate and then the strings to rotate, and that was tricky. So I had to figure out, hey, wait a minute, I can do 2 cameras on the same screen. Why not? So first thing, yes, much better to reverse rotate the camera. Second thing, to generate that actual rotation, to do that, well, a lot of people, most people, actually still do. The graphics textbooks all say, cross product, find the axis, trigonometry, some transcendentals, even worse than those square roots, right? You're absolutely right, and we're going to be talking about rational and I like, that's why I think I divided by, well, maybe up ahead, I divide by the norm squared, not the square root. I don't normalize because I don't like square roots any better than you do. So arc sines or arc cosines for the angle, or Rodrigues matrix, and find the matrix from the axis and the angle, or the geometric axis angle formula. They're actually the same. Or you could do the Quaternion way. The Quaternion way, you can find the cosine of theta over 2. That might actually be involved a little bit, even if it isn't. Even if there are other ways to get cosine theta over 2 and sine theta over 2, to do a Hamilton's conjugation of a quaternion to get a rotation, the first one's a pure vector, only 3 non-zero components. 3 times 4, 12. But then you got 4 components, and then 4 times 4, another 16. You got every quaternion conjugation is 28 operations. Matrix times vector, 9. Much better get the matrix. That's why Euler's formula coming up to go from S3 to SO3 to get quaternion matrix that Euler had, he didn't have the composition, but he definitely had the quaternion to matrix algorithm is much nicer. So you could construct that and use what I call Euler-Schumacher S3 to SO3 quaternion to matrix plus 9 vectors to multiply. And people do scale, so they rotate the points themselves. So there are lots of bad ways to do it. And in fact, I'll show you a picture from a Google Tech Talk from InventSense, all about showing how great quaternions are. And they say, find the angle and then put it into Euler rotate, make the matrix. They miss the quaternion to matrix thing. So a lot of people misunderstand the thing. That is a good thing. Okay, here a little detour into linear algebra, I guess. Orthogonal reflection across a subspace. Generally, you can decompose any vector in Rn into a vector in a subspace and orthogonal to that subspace uniquely, right? Okay. Reflection across a subspace just says reverse that orthogonal part. V plus E to V minus E. Here I'm saying C times V because I'm going to take a unit vector sometime. And so that's, well, how do you get from V plus E to V minus E? It's you double twice V plus E and then minus a V, and you got V minus E. I think, over 2 something. Here it is. So here's the beauty. Here is reflection across a unit vector. Is a reflection is orthogonal. Pythagoras, perpendicular. It preserves lengths and angles. A reflection is an orthogonal distance-preserving transformation. But why isn't it a rotation always? Because it might not be orientation-preserving. It's -1 on the orthogonal complement, so it depends on how many dimensions there are. If you reflect across a line in 3 dimensions, you have 2 orthogonal dimensions. Okay? That's 2. -1 to the 2 is +1. And a reflection across a line is actually a rotation, 180-degree rotation around that line. You'll see this in a second, because all pictures. There's orthogonal projection. I want to break something down into a multiple of V plus a residual E, and I want that residual to be orthogonal. That derives immediately the formula for orthogonal projections onto a vector. And then you Graham-Schmidt and you can do it term by term, but that's how I like to let students divide. Just say, I want something along and perpendicular. If the error has to be perpendicular to this, it pops out. So, here, now we get back to pictures. What does this have to do with quaternions? Well, how do you, reflecting across a line is a rotation itself, but reflecting across a line twice, no matter what the dimension, any reflection twice is a rotation because if the first one wasn't orientation preserving, twice it will be. Okay. So here's the cool picture, cool animation now. If I want to rotate the plane containing these 2 vectors from U0 from noon to 4 o'clock, how do I do it? I suppose I just use that dot product and reflect across U0, reflect across noon and reflect across 2 o'clock. Reflect across your first unit vector and reflect across the sum or the bisector. And let's see if that works. So first you're going to see that the reflection, I'm going to play this movie. You're going to see that this reflection is a rotation. So I'm going to rotate around noon. See that? There. Now I'm going to rotate around 2 o'clock. What did I get? I rotated the watch from 12 to 4. Twice as far. That's the 2 reflections is rotation. Now I'll do it fast. I won't rotate around. I'll just instantly reflect. See, I reflect across that. Now I'm going to reflect across that. That.
Yeah.
Rotation by twice the angle. There it is. Reflection by across 2 things is a reflection, is a rotation of the. Now, I always said, well, doesn't the same argument say that reflection across 2 o'clock takes this to this, and reflection across the final vector fixes the orientation? So yeah, it does. So you can do this first in bisector, or bisector then second. Okay? And hey, if it's those 2, why not 3 o'clock and 5 o'clock? Reflect across 3 o'clock. Reflect across 5 o'clock. What did I get? I still got the 4-hour rotation. To me, that looks like an equivalence class of ordered pairs. Not only that, I could reflect across this, or I could reflect across minus that and get the same rotation. That's a unit quaternion. An equivalence class of ordered pairs of unit vectors in R3, sharing the same dot product and cross product. And the rotation, you don't do Hamilton's conjugation, you do 2 reflections across the 2 vectors. And you get the double angle rotation. And that's a great algorithm. But it shows so much more. First of all, I immediately see that if I reverse one of the vectors, I get the same reflection, right? Reflection across this is the same as reflection across its opposite. What happens to the dot and cross product if I negate one of the vectors? They both get negated. The scalar and vector part are negated, but I get the same rotation. That's the negative quaternion that has the same rotation. Okay? Aha. So I want to understand all other things from this point of view. Trackball math. This in Vincent says do the arc tangent and plug it in. So people don't do this. This is Chen's original trackball patent. Doesn't do this. Here's Schumacher's arc ball. Kind of fun to see. This is a contrast. This is quaternionic, so you see the double angle, and it's path independent. See the arc? It even shows the arc on S2. And nice thing in a way is you can do the full flip with a half rotation, but it's totally path independent because it just keeps the original what you put down watch. I can flip it over full turn with a half turn. Yeah, so that's Schumacher's arc ball. So it's different. An equivalence class of ordered pairs I learned about in Andy Gleason's class. Can we compose rotations by the same construction we use to compose translations? If reflect across this is one quaternion, reflect across this is another, how would I compose them into 2, into a representative of another equivalence class? Any 2 planes in R3 meet. So I can find out what happens to those 2 reflections across the common unit vector. They cancel out. There you get the composition. In which case, quaternion multiplication, we suspect, is the relationship between dot and cross product of any 3 unit vectors in R3. If I know the dot and cross product of this, the dot and cross product of these 2, the dot and cross product of these 2 should be related as quaternion multiplication. That came out of graphics. Can we interpolate rotations the same way? How do you interpolate 2 translations? Instead of having the tail of the first be the head of the second, you have them both have the same tail and interpolate the heads. So I'm going to just find the same common starting vector and interpolate. I've reduced S3 interpolation to S2. I can do quaternion interpolation by doing an arc on literally S2 in R3 instead of S3 in R4. It's faster. Can we, going the other way, gee, this double reflection thing is really nice. Does that work back in translations? What if I reflect across the tail of a vector, then reflect space, points in space, everything goes to its mirror image across the point, the head of a vector? I get a translation by twice the length of the vector. The analogy works perfectly. If I reflect across this point in space and reflect across this point in space, I end up, this point goes
Just
twice
twice
as far.
yeah.
It all goes through.
So,
And finally, can we understand through this view, can we understand unit quaternions, the 2-to-1 map of S3 to SO3, which I already had, and the tangle trick homotopy? Yes. So here I actually made a concrete viewing a quaternion as a pair of unit vectors. Here's this quaternion. Here's its first vector, that. Here are the two vectors, and I can change the representative. I have a button to change the representative. I have a change to negate and invert. What's the inverse? Reflect across this, reflect across the first vector, reflect across the second vector. How would you invert that? Reflect across the first vector, reflect across the second. How would you invert that?
second.
Opposite order.
Yeah.
Reflect across the second,
Second,
reflect across the first. What happens to the dot product? The same. What happens to the cross product if I reverse the two vectors? Negate.
It's the negate.
Conjugation. Negate the vector part. There you go. So I see quaternions explicitly, concretely, with respect to a basis. See, I can rotate my thing now because I'm using this. This actually generates all the 1 decimal unit quaternions. Exact 1 decimal digits by finding all the 4 integers whose sum of squares is 100, and then divide by 10. It was kind of fun. Numerical number theory. Okay, so negate, invert. I can show you all this. 2 reflections, doubles, translations, and plane rotations. So the null homotopy.
Oh, yes.
Where is it? The book.
The book, oh, that's the gravitation, yeah.
Yeah.
I
Is
don't
it there?
have
I thought I had it up here.
Oh, that's a big book, I know this.
Ah, there it is.
Yeah, that's the Bible.
This came to me
Telephone book.
This came to me one day, wrapped in a thing that says, if you read this, you'll understand why it's so heavy. Remember that? And in it is an amazing picture that says if you take a ball in the center of the room and do this, and so I also tried to make simulators and stuff with tape and pens. About half the time it worked, half the time it didn't. I don't know. So I had to try and understand it better. But here's the point. Okay, let me go ahead. If I reflect across a unit vector and reflect across the same unit vector, what transformation of space do I have? Reflect across the same thing twice. Yeah, I did it. Yeah. So if I take a path of a second vector on S2 that starts and begins at the same vector as the first reflection vector, the start and the end will both be the identity. If I do my second reflection on an equator that goes, I've gone pi over 2, a quarter turn, pi over 2. They should really have a different thing that would make that a quarter. What would you call it? Maybe tau or something. Anyway, you do a quarter turn, double the angle. We already saw why it doubles the angle. If I do a quarter turn, the rotation is how far? If the reflecting vectors are a quarter turn apart, how far apart are is the rotation? Half turn. Right? 90 degrees, 180, 30, 60. Right? We saw the double. That's the clock, 2 o'clock, 4 o'clock. So if I do take my reflector 1 turn around the equator, how far did the rotations go? Twice. So now I just do the rubber band homotopy on S2. Whatever it is, it's a morph from 2 turns about the vertical axis to a constant at the identity. And it turns out to be David's beautiful homotopy. He figured out that they're the same. And so here what you see are the paths. Equator. Whoops, I have to push the button. So another way to see, so there are my paths on S2. That generates a belt trick. Yeah. But that's the path of the second reflecting vector where the first reflecting vector is always that. And if they start and finish there, it's very explicit. Again, a good vector geometry thing. Find the intersection of a plane with a sphere. A plane centered at E1. See, I know what that is. I'm taking a plane going like, whoop, and I'm getting those paths and parameterizing them. So, Here you get belt trick. Two full turns of the belt down here along the path of the belt. The edges are both the identity, represented by a square, the image of a square. And now run it. Here's my belt going from 2 turns through the homotopy, slicing this way. And at the end, you will get the flat belt from the literal homotopy square. The plate trick is vertical slices. And same thing, there's the 2 turns. My camera flipped up so you can have this be 2 full turns, 1 turn and 2 turns. Straight arm, twisted arm after 1 turn, and let it run. And here you go, oh, there's your homotopy version of the plate. Here's tangle trick, and this is the one in Misner, Thorne, and Wheeler.
Yeah.
Johannes, you can be the ceiling. Hold this. You translation, but no rotation.
You want me to
Good.
hold this?
Hold that. Give me slack if I need it up a little bit. Let's get it flat. There.
Okay.
Perfect. Okay. Now I'm going to do 1 full turn. Whoops. I have to step on this.
Oh, be careful.
Here. Good. I'll use my knee this way. Here. There. Okay. Ready? 1 full turn. 2 full turns. Give me a little slack. Belt trick over. Belt trick under. Fortunately, they go around. They chase each other around. And that's it.
We are.
That's Misner, Thorne, and Wheeler. Here it is in homotopy land. It's reflected. It's twist this way, twist back that way. If you put twists in ahead this way and in the same orientation, it wouldn't work because one would be trying to go this way, one would be trying to go that way. So that's for topologists. That's one you will be able to explain why if the 2 turns go this way and the 2 turns go that way, you can't do it without a collision. There's an obstruction, I think. I don't know. So it's reflected. So here's another way of doing it. Instead of the cubes, why not reference rotation of a sphere? Not only a sphere, concentric spheres along the path from an inner sphere to an outer sphere. Well then, there's no way paths can intersect because it's rigid rotation at every radius. If it's the identity, it's just radial lines. If it's 2 turns about a vertical, they're going to wrap around the sphere twice. And the homotopy is somehow going to unwrap it. Okay, I think we got to put the 3D. You could put the 3D glasses, but I can send you links too, but there it is. You have an outer sphere and an inner sphere, and it's just literally the path of the homotopy of a single point in the homotopy. And this is 2 cameras, if things aren't moving the same. And you can do it 2 turns, or 4 turns, or 8 turns. So the 8-turn one looks pretty cool. And you can change your view on it. You can actually do this in a virtual trackball and watch it from different angles. Okay, so I can send anyone a link for that. Okay, here, doing them with a fixed point, looking at that, here are my 2 turns, and the identity going across, and this was paths in R3 that represent, the position in R3 represents the axis, and the distance from the origin is the angle going essentially from 0 to 2 pi at infinity, so the R3 plus the ball for S3, and so that's an early Java representation.
But Bob, isn't that happening in aren't you just using an R2 slice of R3 for the axes?
I'm using an R2 slice of R3 for the axes.
Okay.
Exactly. That's you're literally seeking the plane. And what you're doing is you're going from 2 turns, which is at infinity, to the origin. So you're doing a reverse contour integral. You're making R go to 0 from infinity. And as David noticed, it pauses for a long time while it's waiting to come back in it's exactly what he was talking about yesterday, about that going out this axis is the same orientation as going in the other axis, going in from minus infinity on the opposite direction. Very beautiful that he came to, and we could wave it yesterday all the way through, which was amazing. we had lots of correspondence before this, and I learned a lot more about my own homotopy, my version. So the origin of this was then, what is the formula? Could we derive from the geometry the relationship, if you know the dot cross product of this, the dot cross product of this, can you get the dot cross product of this? So I was thinking, what's the structure, just like what is the structure of complex multiplication in the circle rotation? Rotation in the circle, I'll probably try to be out in about 5 minutes, I think is about right for, so notice that how I'll teach in class complex multiplication. If 1, 0 goes to xy, then just turn your head, this becomes 1, 0, this becomes minus yx. And then x0 goes to x times xy, y0 goes to y times minus yx. Add them up, there's complex multiplication. And so the cosine addition formula and the sine addition formula, done. So I wanted something that would show the structure. So complex multiplication is x times xy plus y times minus yx, capital and small. This was an article in the notices and a little thing. So from that, once you have that, that's rotations, not only that, this also gets you x squared plus y squared equals 1. Because if 1, 0 goes to xy, x negative y goes to 1, 0. There's Pythagoras as cosine theta minus theta equals 1. Cosine addition formula. So that's all trigonometry in the can in the way. So you can get the geometric interpretation by explicitly rotating to a standard configuration. I can rotate any one vector so that all but the first coordinate is 0. Second vector, so all into the xy plane. All but the second vector. The third vector, I can make all but the first 3 coordinates 0, and so forth. That's QR, really. That's the QR orthogonal triangular decomposition. We get a proof of Euler's theorem from this, actually. So here I made a composer. Oh, this is ij equals k. The equivalence class j. J comes first. I circle j, so j comes first. That's j. Dot product 0, cross product 0, 1, 0. I will be dot product 0, cross product 1, 0, 0. This is the scalar part, vector part. And you compose them by that first of the second, second of the first, drop them out, first of the first, second of the second, there's k. No. But I made a much more interpolation. Interpolation works. Put the first vectors the same and interpolate. I'll actually show you. Here's interpolating quaternions geometrically. Common first vector, second vector here, the dot product is this, the cross product is this. And now I will interpolate that. How do you interpolate? You just interpolate the second vectors on S2. It reduces the dimension for interpolation when you view quaternions this way. There, interpolate. So those are the interpolation on S3, literally. If you look at the 4 components, so squares, it will be. Here's composition, concretely. Kind of a fun thing about this is, so here are a few, it's a little calculator thing that I've got there that you can, I guess we take this off. You can choose a scalar quaternion, an elementary ijk plus or minus, a vector with scalar part 0, or a general one, and you just click through and it'll get them all. So you can actually see quaternions and their composition product. So I'm gonna go through, not a unit, not a problem. I was like, I wonder, well, let me see what happens if I put a non-unit quaternion in. No problem, I can scale the 1 to a 2. I can scale these to 3 and 4, for instance. And it's just, my representative vector, the algorithm just did it automatically, and it actually works. So general quaternions. Hamilton on Rodrigues and Hamilton. He wrote, wisely, Rodrigues in his thesis had a better understanding of the algebra of rotations than Hamilton did. So I thought maybe he could give me a clue on finding the formula. Here are pictures, and some important parts have been translated by RSP. Because my French isn't so good, so the law of composition, the resulting axis must be placed in such a way that when carrying out the 2 indicated rotations around the supposed intersecting axis, it comes back to the original position. If therefore, through each of the given axes, one places a plane that makes with that one of these two axes an angle equal to half the rotation relative to this axis, then the intersection of these two planes will be sought for the resulting axis, arriving by virtue of the first rotation in its position symmetric with respect to the plane, and the two axes arriving back. And if you reverse the order of the rotation, the axis comes differently, and he talks about that. He actually talks about it. So here you, let's just say, what if you rotate this one forward by half the angle, the same vector to an orthogonal vector in its plane, and backwards, an orthogonal vector in its plane. Take their dot and cross product. You get quaternion multiplication. Take their dot, take their cross, it just pops out. Thanks to Hamilton, is exactly what he said to do. And it's Gibbs inspired. So here's his composition formula where he wrote that exactly down. There it is, and that, there's that. And he actually even, I only noticed that just recently from Father's translation, characteristic, moreover, there is between these two sorts of composition and analogy, the rectilinear triangle for translation, the spherical triangle, and the signs of the half rotations, the signs proportional to the signs of the angles. So he actually wrote about the spherical triangle for rotation.
Exactly.
Oh my gosh. And then here's his axis thing. And he also talked about the angle. Here's the formula for the angle. Except I don't know if I trust anyone who thinks a full circle is 400 degrees. Maybe it's grads. But anyway, and so the same angle, and he talks about the non-commutativity. He says if you do it in this order, that the axes are symmetric across the line between the axes. He actually writes that down very explicitly. And that's there. Axis symmetric, so I'm running through that. It wasn't that obscure. It was in this journal with Cauchy, with Blanchet, with Cauchy, Delaunay, Liouville, Lebesgue. Apparently that's not the same Lebesgue, because apparently the same Lebesgue lived a lot later. Catalan, and Olivier, and Lamé, Delaunay. So this was kind of, not only that, and just like Johannes discovered, Dick Haley wrote about him, not only in 1845, but in 1843. And these are both originals. There's an original, I think I had the other one. Louville's journal he talked about in the 5th volume, and stuff like that. So there are here just both of Rodrigues's and Euler's. This is Euler's matrix from axis and rotation, and this is Rodrigues's, which are fun. Here's Euler, had the map from Quaternion matrices. There's the 3 by 3 components, the map from S3 to SO3. So he did this part, and Rodrigues figured out the thing that made that a homomorphism, I guess. And where did theta over 2 come? This is the last slide, I think. Where did theta over 2 come from? If you look in the Lie algebra, theta times the axis, and you exponentiate it, you get the rotation matrix. Now, theta times the axis, once you get to the ball of radius pi, you exponentiate it. At this end, you fall off, and this end, and they're not periodic, so it doesn't come back. Big problem. So what if you tried sine theta times the axis? Well, the problem is, when theta is pi, you lose all your axis information. And even when it doesn't, you lose, it's 2 to 1. So there are two things with the same sign. Watch. Bet you didn't know this. There are two values on the circle with the same sign. Yes, you know this. So all the way up. How could you fix that? Let's cut this here and shrink it here. And this will be sort of the last thing I'll probably say, is cut that, bring it back to half, but make that map, theta over 2. Suddenly, this is 1 to 1 from your sine theta over 2. Sine theta over 2 times the axis, unit axis, if you think of it as in the northern hemisphere, is a 1 to 1 map, is 1 to 1 with 3D rotations, with SO3. Sine theta over 2. SO3 sits in the unit quaternions in its vector part alone. I mean, you can basically solve for the scalar part if it's a unit quaternion. Square root of 1 minus sine squared, plus or minus. And so that's why you got to double it. And that's how Rodrigues ended up figuring out, oh, if I want to make this continuous again, but still periodic, double it, then I'm done. And I think I'm done too.
Guess what?
I am done.
Thank you.
Excellent. Okay, You have 1 minute, but we'll ask some questions. Anybody have any questions for Bob? Any questions? That was really, really wonderful and comprehensive.
Thanks for being the ceiling.
No problem. Anyone have any questions for Bob? Okay, I think we can put the light. Oh, there's a question over there.
So Bob, let me just share an idea that is directly related to something on one of your slides. I think you know because we've corresponded about this, but at one point a few slides back, you talked about how one can think of a unit quaternion as this pair of unit vectors under an equivalence relation.
Yes.
The equivalence relation, you expressed it as same dotted cross product.
Yes.
But that's equivalent to saying that the angle between them and the plane they each pair determines is the
Unless
same.
they're parallel, then it can be any direction.
Yeah,
Right.
and
Or
so
it's parallel.
what I found
Special
absolutely
classes.
fascinating, and I didn't know this way of thinking about it until I read Hamilton. So I've been in the business of reading Hamilton for the past few months, as I think you know. And so I read quite a lot of his first book, his Lectures on Quaternions, which is, I don't know, 500 or 600 pages anyway. If you read the first several chapters, you find out what his view of how he presented quaternions was. And it's completely unlike how we think of quaternions today. He never gets to talking about even addition of quaternions or associativity of multiplication or even the quadruple coordinate interpretation
But he
until
talks
much
about
later.
dividing vectors.
But he instead introduces quaternions essentially as we could think of it as introducing them as these ordered pairs of unit vectors.
Right.
And his point of view there is that this is how you should think of a quaternion as being a quotient of vectors rather than any other way. So I found it fascinating that to him a quaternion.
And I suddenly realized what from
quaternion is a quotient of vectors,
Yes.
and it's fascinating that he
and
approached
so
it
is a
not from the point
difference.
of view of
It's
addition
a
or subtraction
VW
or
inverse,
multiplication.
right?
It's quotient. It's about how you get from one thing to another.
Right.
And if you think about how you get from one thing to another, how you get from this vector to this one, you're essentially talking about a quotient. So the fascinating thing is that he introduced them
in
as
translation,
quotients.
the difference, and I hadn't seen that.
So I was blown away to
Right.
find out that to him quaternions are quotients of vectors.
Formally, it's VW inverse. Whether that's addition inverse, then it's our 2 points is this equivalence class. And you can formulate it, instead of formulating it as dot and cross product, I can say these two are equivalent if and only if there's a rotation of space that takes this one to this one and this one to this one, just like a translation that takes this point to this point. So you can, and that's probably where he was going to.
And this leads to that spherical arc interpretation that you
Right.
didn't talk about here much, but which he then talks a lot about.
Right, but I was amazed to see that Rodrigues actually really wrote spherical triangle and that thing.
That's
Like,
right.
and so,
That's
so I think we should team up to translate. I think because we've
That's right.
got a nice
He did
start.
write it. He did write about it, and he wrote about spherical geometry too.
Yeah.
He mentioned about that. Yes.
Let me know if I can send you links or anything to these animations. They're making an article coming, and keep your 3D glasses because I can give you a link, or just look up
That would
3D
be really
Explorer
nice,
Math.
yes.
It's a fun thing great for teaching and outreach things too. Okay.
Thank you.
Okay, that was really good.